let's talk about Quicksort in this video. Quicksort is one of the fastest comparison-based sorting algorithms. It runs in O of n log n in its best case and average case. It runs, although it runs in n squared time when you give it the worst case possible, and I'll try to show you why that is in a second. The unique thing about Quicksort is the concept of a pivot point, where at each particular step you choose a pivot point upon which to arrange the elements around, and I'll show you how that's done in a second. The code that's to my right comes from the Rosetta Stone website. You can just go there and search Python Quicksort, and you should arrive at the code that you're seeing on the screen. What does Quicksort do? Quicksort is a divide and conquer style of sorting elements in a list. So and as we have discussed in the previous video, if you have a divide and conquer strategy, the first thing that you might want to do is to identify a base case. Now, in the case of lists that you want to sort, what are some possible base cases? Well, we might say that if you have a list and nothing's there and you ask me to sort it, just return nothing because there's nothing to sort. Similarly, if you have a list with one element, say for example 3, you just return that element when you ask me to sort it because there's nothing really to sort. These are the base cases of sorting algorithms and is also the base case for Quicksort. Where can we find that in code? Here, where if the length of the array, this is my array, if the length is 1 or nothing, you just return the array. So you just return what you have, and that's already sorted. Else, what do you need to do? You need to assign a pivot. A pivot in this particular example is conveniently the first element in the list. You can do it randomly, but for this particular code, it says, or it tries to use the first element as pivot. Now, what do you do after that? When you have a pivot point, you create a list called less, or name it whatever you want, but the intuition is you put the numbers that are less than the pivot point here in this list. The numbers that are more than the pivot point, you put it here, and you recursively call Quicksort on the less and more lists, and then you return less plus pivot list plus more. Let me try to tweak this a bit so that it helps with our tracing. Instead of returning that, I want to combine lines 1 and 2 with line 3, where I return the Quicksort of the less plus the pivot plus Quicksort of the more there, so that we can trace it in code. How will that work? Say for example, I have a list composed of 9, 4, 1, 5, 7 there, 9, 4, 1, 5, 7, and I apply Quicksort to it. Let me try to place it somewhere at the center. I apply Quicksort to the list 9, 4, 1, 5, 7. Okay, now what do I get? The first thing that I need to do is to choose a pivot point. So for me, or for the code, it asks that we choose this. Okay, now if we have chosen that as pivot, then we know that we don't call the Quicksort function on that, but it occupies the center upon which you will try to append the lesser numbers and the greater numbers to it. So 9, that's our pivot point. What are the numbers that are less than 9? We have 4, 1, 5, and 7. So let's put that here. 4, 1, 5, and 7. What are the numbers that are more than 9? We say there are none. No numbers are more than 9. What do we do now? We know that we have to recursively call a Quicksort on the left side, and the right side. But here's something interesting. We have found a base case. This is a base case because we have identified that if the array that you're trying to sort contains nothing, then you just ignore it and return nothing. Okay, now what do we do next? If that is the case, then what we do next is let's try it. I'm searching for my black ink. Let's put in let's put in pink the numbers that are already sorted. So 9 is already in its sorted place. The intuition is after being the pivot element, that particular element is already sorted. So 9 is already in its sorted place. We now try to apply a quicksort on the list on the left. So that means applying quicksort here, that becomes our new pivot element. And so if that is our pivot element 4, we try to write the numbers that are more than 4 to the right. So plus, this is what's more than 4, 5 and 7. That's its own list. What's less than 4 is 1. And of course, the pivot doesn't receive the recursive call to quicksort. The ones to the left receive a recursive call to quicksort. The ones on the right receive the same call as well. And then you just have to append everything. Okay, now interesting again is this one, the call to quicksort on a single number. If that's the case, then we just return the number as is. In effect, again, once you reach the base case, the intuition is I have already that part of the problem, that smaller part of the problem is already solved. So we can already write 1 in pink because that part is already solved, similar to 9. And because there is no recursive call on P as well, the pivot point, and it gets returned, we intuit that that is already solved as well. So 4 may be already written down in pink ink as well. And we're just waiting for the append to execute, but it's not executing yet because there's still a recursive call to the quicksort function. Let's continue. 5 would be the new pivot point. And being the new pivot point, we say 5 is the pivot point. I want to write everything that's less than 5 to the left, which is nothing. I want to write everything that's more than 5 to the right, which is 7. Recursively call quicksort on the left side and the right side, and cool, we both have base cases. The quicksort of nothing is nothing, so that's already sorted. The quicksort of one element is itself. If we try to write in pink those that are already in its proper place, since 5 is the pivot and no recursive call is going to be called on it, it's already sorted. Since this is part of the base case, whatever gets returned by the base case is already a solved sub-problem. This has been already solved in few iterations, and now we have a solved list, which is pretty cool. So that is quicksort. That is what happens when you implement quicksort. In the next video, I'll try to show you why, and sorry I wasn't able to cover it. I'll try to show you why in the worst case this is O of n. But we can see now that this is n log of n. We had five elements, but we needed less than 5 1 2 3 4 1 2 3. We needed less than 5 iterations to actually solve the problem. If this scales more, and I'm sorry I will not be able to show you, if this scales more, say for example to 1,000, we will notice that there is a log n number of iterations needed to sort the elements in that list. So thank you for watching. I'll see you in the next video to discuss why quicksort is worst case n squared. Thank you for watching. Bye.